So for today's session, we have one of my close friends, I would say, Dr. B.S.R.V. Prasad. He is presently working as Associate Professor at Department of Mathematics, Vellore Institute of Technology. So Dr. Prasad will be speaking to us on the topic food supplementation for predators and parasitoids, a double-edged sword. So a brief introduction about Dr. Prasad. Dr. B.S.R.V. Prasad is a mathematician specializing in mathematical ecology and biology. He earned his PhD degree from Andhra University, driven by a passion for research that led to him leave a teaching position. His work focuses on developing mathematical models to understand ecological interactions, particularly prey-predator dynamics and their role in the biological control and conservation. He has also contributed to interdisciplinary projects like the Chilika Lake ecosystem, collaborating with zoologists to develop these models and understand the underlying biogeochemical process in the lake. Currently, as I mentioned earlier, he's an associate professor at Vellore Institute of Technology. Dr. Prasad's research has been recognized with numerous awards, including Young Scientist Award from DST. He executed a research project of 10.56 lakhs, for which he was awarded the Young Scientist Award. His findings have been published in prestigious journals. He actively shares his knowledge through talks and presentations at international conferences. Notably, he has visited Max Planck Institute of Evolutionary Biology in Germany, the Mathematical Biosciences Institute at Ohio State University, which is located in USA. He has also mentored and in fact guided PhD students. His work exemplifies the successful application of mathematics to address complex ecological issues. With this brief introduction, I hand over the stage to Dr. Prasad. Over to you, Dr. Prasad. Thank you. Yes, your slides are visible, Dr. Prasad. You are on mute, Dr. Prasad. Can you go ahead?
Yeah, I hope now you are able to hear me. Yeah.
Yes, perfect. Please go ahead.
Okay.
Please go ahead.
So first of all, let me thank Dr. Vamsi for inviting me to give my insights in this popular science talk. And also I am grateful to the Satsai Institute for Higher Learning Authorities for giving this opportunity to present my work in this Center for Excellence in Mathematical Biology Popular Science Talk Series. So today I am going to talk about something on food supplementation for predators and parasitoids, a double-edged sword. So I'm just working on this from long past 10 years. I'm working on this field. And actually, this is one of the areas I like very much because this is actually related to controlling the pest, agricultural pest, without using any pesticides and insecticides, which is actually the one of the environmental friendly way. So India being a heavily dependent on this agricultural, and I feel this type of research and this type of techniques are very useful or very needed for this present India. So hopefully that this biological control is now actually gaining a momentum in India, but this is gaining more momentum in the foreign countries like USA and even in Germany and what is that UK. And I got these insights of all these experimental works. I got them from their researchers that have happened in Europe and France, all these things. From there, I tried to develop these models. So my intention here is to see that how mathematics can be applied or useful in studying these complex ecological systems, and how we can implement some ecological or conservative strategies so that we can achieve the goals in a minimum time, or what are the needed things to be doing this one. So after this brief introduction, let me go to the first thing, what is actually meaning of biological control. So before that, this is one of the slides I like very much, and I put this in each of my presentation, which says actually how mathematics is top of all the sciences. This is one of the slokas in from Upanishad. It says that Yada Sika Mayuranam Naganam Manayom Tada Tat Vedanga Sastranam Ganitam Muddhinim Sthitam. Which says that as the crest on the heads of the peacocks, as are the gems on the heads of the serpents, so is the mathematics in the helps of sciences. So it says that mathematics is everywhere. So which I'm just going to use that mathematics and try to solve or give some insights about what is the biological problems, how complex problems can be solved. And part of this work supported by the DST in SERP under the Young Scientist scheme. So I should acknowledge them for giving this opportunity. So now let us go to the introduction. What is a pest? Pest is actually nothing but any organism that is detrimental to humans and environment. It is something like damaging crops, injuring or irritating livestock, or reducing the fertility of land and spreading vector-borne diseases like mosquitoes. All these things comes under pest. So we want to control this pest. So we are having so many control strategies. Traditional control strategies such as mechanical control, where we are using gadgets, traps, and machines and other physical methods. And cultural control, where actually we are trying to alternate the crop from one season to another season, rotating the crops so that the pest will not be having a regular, they cannot survive regularly. So we can reduce the pest. That is what called cultural control. And chemical control, and this is widely used nowadays also, that is pesticides and insecticides, using insecticides. But this control, chemical control, has its own drawbacks, and in fact it is environmental not friendly, and many times these chemicals will be getting into the food items and which are actually contaminating the food and which actually causing lot of damage to our health also. So many countries are actually trying to reduce this use of chemical controls, insecticides and pesticides. So that's why they are actually going for the other technique that is called biological control. So the biological control can be defined as use of one or more organisms naturally, these are called natural enemies, to maintain other organism which is called a pest at a level at which no longer problem. So we want to not to completely remove a pest, but we want to keep that pest in a position where it is not at all completely problem to the environment. So here the term pest is used in a general sense that that any organism that damages or injures or irritate livestock or man. The natural enemies can be either predators, parasitoid, pathogens, all these things. And another one is this work, actually this biological control definition can be used for mosquito control. So it can be used in vector-borne diseases also. So that's what the definition of biological control present here exclude transgenic and genetic technologies where the pest itself is genetically modified for the purpose of population reduction or population suppression. I'm not talking about genetic regulations, transgenic regulations here. I'm just talking about introducing some natural enemy to control a pest. And actually the control type, there are several types of biological control that are there. One is classical. The first one is a classical, which is called introducing a specialist or natural enemy in the pest habitat. So when there is no enemy is not there, so identifying a proper enemy and introducing that in the classical, in the environment. But this has its own problems. The introduced pest or a natural enemy can later become a pest. It is one of the example happened in the UK where they are introduced some feral cats that becomes a nuisance to the entire environment. They produce and they become a pest here. So this is one of the classical approach, but this has its own consequences. Next one is inoculation, where number of natural enemies are released at intervals and allow them to reproduce but not persist. That means we are going to introduce the natural enemies, but they will be allowed to reproduce, but after some time they will not allowed to persist. That means we cull them or we kill them after some interval or the pest is removed. And inundative, where releasing a large number of control agent in a such rapidly such that no pest reproduction will happen, and reproduction for natural enemies also not happen as expected. And the next one is the conservation. This is what actually I am talking about. My work is entirely related on conservation. Is the conservation is nothing but we want to modify the environment in such a way that the natural enemies will be sustained more and they will control the pest in the required way. So maybe by altering the environment, maybe providing some more suitable conditions for the natural enemies to persist. So we are going to uh, do some modification to the habitat so that the pests can survive long. Sorry, the predators can survive long and pests can be suppressed. So there are the success of biological control depends on whether what type of natural enemies are there. There are two types of natural enemies. One is specialist, another one is the generalist. A specialist is nothing but which is specified to or which is actually feeds only one special type of pest only. It will not feed all type of pest. So a great attention has been what is that? Attention has been paid on to the specialist on the biological control. But the drawback of the specialist agent is identifying them, releasing them, and using them is felt is on consequences, because we may not be able to find the specialist every time, and which is able to feed on that one. And maybe if you feed that also, we may not be able to reproduce them with the enough numbers. So it has its own drawbacks. So then we comes to the generalist predator. A generalist predator is actually lacks the prey specificity. That means it can take any food, whatever available, and and have longer generation times. That means the reproduction times are longer, and it can prey on more prey. But this again has some other drawbacks, such as because these are generalists, sometimes they will try to deviate from the original pest which is actually damaging the crop, and they will try to feed on the other pest which is not non-damaging. So how to avoid this? How can you use this or these modifications or generalist? How can you use the generalist and control the pest is a challenging aspect. So, and because generalists are polyphagous, they depend on many non-pest food sources such as plant materials, nectar and pollen. Actually, many plant species will attract this generalist by releasing this nectar pollen, so that they will actually, it's something like a mutualism comes into picture. So the plant will provide some food to these generalist predators, and these predators will in turn help the or in turn act in such a way that they will control the pest or they will control the damages that are caused by the prey species. So there is a there is some technical issue. Audible? Audible now?
Yes, sir. Yes, sir. Yes, Prasad.
I don't know. There is some technical issue. I think.
Yeah,
Sorry for
some
that.
for brief time. Yeah, it will.
Sorry for that. These generalist predators actually depends on many sources such as alternative or additional supplementary sources. Now we have to investigate that how this effect of generalist predator feeding on other food sources affect the biological control programs, whether it is beneficial or not beneficial. So the experimental work done in this case says that the answer is not always true. It's a mixed answer. That means sometimes they are achieved that the providing supplementary food or additional food to the predators actually helping the predators and to control the pest, or sometimes it is actually having other consequences such as the pest is dominating and there are situations where the entire predator is gone extinct even providing the supplementary food, but pest is dominated. So there are actually a lot of consequences. There are two effects. One is positive, another one is negative. They are actually having, and how this is happening, why this is happening. That is the most important feature. If we can understand this, then we can accordingly we can derive the control strategies to control the pest. So, and again, one more happens is because of this polyphagous nature of these predators, there are a lot of other complexity comes into things, such as this naturally becomes cannibalistic. That means because there is, when there is a food shortage is there, because there are actually polyphagous, they will feed on their own juveniles to survive. The adults will survive. So there is a cannibalism comes into picture, and because of, and one more is because there are a lot of feeding is happening on the pest. The pest has its own dynamics, such as they will have a group defense, or they will sometimes adopt some anti-predator behavior. That means some of the pest species sacrifice themselves, killing the juveniles of the predators, so that their generation, next generation of the pest will survive, and so there is a anti-predator behavior also comes into picture. And another most important factor that can comes into picture is habitat fragmentation. So nowadays this is actually happening very quickly, because one species, one habitat to another habitat, we are hatching different crops, and even we have having lot of landscapes are changing into picture rapidly. We are changing the landscapes, so the habits are actually become fragmented. So one species surviving in the another one habitat may not survive in the another habitat. So this is actually happening here. So this also plays a crucial role. So how to handle this habitat fragmentation, cannibalism or group defense, anti-predator, all this with respect to in terms of biological control, and also providing some supplementary food to the predators or natural enemies. And here one more important feature that actually I'll discuss at the end is some of the pest species also become polyphagous. So they also are generalists. So they also can feed on the variety of food, and they also can share the food that we provide to the nectar pollen that is provided to predator. So there is again lot of other consequences comes into picture. So because of polyphagous, they will survive not only on the crop, but they will survive other species. So they will increase, and the crop damage can rapidly increase. So, but how, what is the variety, what type of food we have to provide in that case, so that the pest will not survive much, but the predator will grow and the pest control can happen. So to have to study all these things, we are using some mathematical rule, because experimentation is always a huge task, and it is very intensive process, and it is time consuming, and sometimes we may not be having proper results also. So if we can have some mathematical techniques where we can use some mathematics to have some idea, so the experimental that okay, I can use this type of natural enemy, or I have to use this type of supplementary food to control this type of pest. If we can give some insights, that will be more useful, that will be more practical. So we want to do answer this type of questions. For that one, we are using some techniques such as dynamical systems, optimal control theory, and differential equations. And here, before going to my other topics, I want to introduce some technical terms such as functional response. Functional response in ecology is nothing but the uptake rate of a consumer or predator as a function of food density, and the numerical response is the reproduction rate of a consumer as a function of food food density and associated with the functional response. And actually CS Holing is actually who is the instrumental in deriving this functional and numerical responses. There are generally main three types of functional response: type 1, type 2, type 3. Type 1 is linear, that means they are actually type 1 is related to the density of prey and predator. Type 2 is not linear, it is a non-linear. There is a saturation effect comes into the predator, because we cannot take the food, how much food is available, even our gut also cannot take how much food that is available. So there is some saturation after some time. So that is a saturation effect comes into picture. Type 3 is actually the defense comes into picture. So at small levels, small prey levels, the predator is very, predator will be finding it very hard to find the prey and feed on that. So there will be some group mechanism or escaping or something happens. So depending on that, they will not be able to feed more. So there is something like, it looks like a S curve. This is what is called type 3. And there are some other functional responses also there, that is Bendit and De Angelis, which is actually where there is a predator intraspecific interaction will come into picture, or mutualism comes into picture. So they can fight with each other, or they can interact with each other, and they will waste some time in feeding on the pest or the available food. So this is what Benedictine de Angelis. There is one more, there is a ratio dependence, which has a lot of criticism and lot of acceptance. It is a lot of happened here. The ratio dependency actually, it is actually mainly works for group defense, and it is actually sometimes it predicts that at low prey population there is a stability comes into picture. Remaining all other models type 1, type 2, type 3, and then Benedictine de Angelis will not predict that low prey population the stability will not predict. But in real life, this is what happens. At low prey population there is a survival, there is stable survival will come into picture. But that for that one, the ratio dependency comes into, but the problem with the ratio dependency is it has a what is a singularity at 0, 0 population. So there is a lot of criticism, lot of favorism is there. So if you want to read that one, you can read the articles by Aditi and Ginsberg and Jack. You can read that. So, but in my research and my next, I can show that this normal present models also can show that type of behavior because of supplementary food provision or availability of additional food. So there is a we can give a alternative point for ratio dependency in using this supplementary food support. So to do the general mathematical framework, I am taking N is a prey, P is a predator. So I am using the function response, and I am using the loss and growth and loss response. So using that, f of NPA is actually the what is that prey growth with respect to the additional food and the available resources in the absence of predator, and GPA is the function response, and H1 PA, H2 PA, H2 and PA is nothing but the functional response of numerical responses of predator with respect to prey as well as with respect to additional food, and minus D N of PA is the mortality of predator. So I am going to take this general model, and then I am going to derive the equations, and we are going to discuss about that. And in my research talk and this present talk, I am avoiding many of the mathematical menderings because I want to give a general overview of what happens here. But if you want to go into more mathematics, we can see that it's nothing but a lot of calculations. We have to do all these things. So the first thing is I derive the functional response by using time utilization concept, deriving that small delta t time. We are taking delta ts is the setching, and delta t is the handling time, delta p is the handling the predator by predator, and delta t is the predator handling the additional food. Accordingly, we can derive the functional responses. So we have the functional responses and feeding them in the given equation, and using the non-dimensionalized process. Maybe those who have attended the last session know what is the use of non-dimensional process and what is the importance of non-dimensional in studying the mathematical models. Just simply we are avoiding the complexity or something like a parameter, what is the units of the system, as well as combining the similar parameters into one parameter so that we can reduce the number of parameters also. So now developing a non-dimensional model. So first model I am going to see about supplementary food consumed by predators only. So in this model, the model is given by this. Here I am using X for prey, Y for predator, and Xi is the quantity of food that is provided to the predators, and alpha is the quality or the nutritional quality of the supplementary food. And this alpha Xi plays a vital role here. So actually what I am doing is I am introducing some time utilization concept. From that one we got this alpha Xi, and this Xi is the quantity. That's why we can see that y dot is actually nothing but beta x by 1 plus alpha Xi plus x plus Xi y by 1 plus alpha Xi plus x. So we have two terms. One is from with respect to prey and one with respect to additional food. So there is a additional growth is coming for the predators. But whether this additional growth is always useful or not, we have to see under which condition it will be positive and which condition it will be negative. We have to see that. And if you take xi equals to 0, it becomes a simply Rosenvik-MacArthur model. Many people who are in the mathematics, they know how to, what is the use of this mathematical. This is a standard model, and we can see what is happens in this model. It's actually either we have a stable or we have a limit cycle comes into picture. So now if you do the analyzation, as usual, the equilibrium analyzing, we'll see that the present system admits to one trivial equilibrium, one axial equilibrium point, and one interior equilibrium point, given by x star y star by this expression. And now using the theoretical dynamical system theory, we got all the bifurcation analysis, which I am not discussing about here. There are various bifurcations that occurs in the model, such as transcritical, saddle node, and Hop bifurcation. These will give you insights about what are the various type of food will be useful or with respect to what food, what happening. Okay, if you see this, all this involves alpha xi. All these costs involve alpha xi. Because alpha xi is the control parameter which is in our control, because all other parameters like growth rate, mortality, and what is the number of population, all these are, and the carrying capacity of the environment, all these are not in our control. So I'm going to take alpha xi as a control parameter. So if I vary alpha, if I vary xi, what happens? That I'm going to see that. So that's why I'm going to print them this alpha, these three curves, saddle node, transcritical, Hop bifurcated curves in the alpha xi space under three conditions. What are the first condition is, in the originally, when I am not provided any supplementary food or additional food to the predators, the system is pest dominated. That means the pest is dominating the predator, and predator is not able to control. That is the first condition. In the second condition, there is a coexistence of prey and predator, that is given by delta by beta minus delta less than gamma. That means the mortality by birth minus death is actually less than the carrying capacity, which is less than or equal to some sum of birth plus death by birth minus death. So this is what the coexistence. And similarly, we have another which is pest free state. That means where there is no pest is there. So under three conditions, I'm going to plot the three curves. So if you plot that, we'll get some curves something like this. So we have a alpha axis, we have a j axis. So we have a different regions comes into picture. Here, if you see in the region D11 and D12 or D23, D33, if I take any alpha xi in that region, then the system is pest dominated. That means I don't have any interior point. Every solution will reach to carrying capacity of the pest. So this is the food which I should avoid, because this is actually making the pest dominate the system and predator go extinct. See, you may have a question that why, when we are providing a food to the predators, how the predator is going to extinct. This is in a way I can say that this is the food is actually not, this is a food something like a food which is some additional food, but it is not at all giving any energy to the predators, and predators are wasting the times. In a way they are stupid predators. That easy, because the food is easily available, without fighting with the prey, they can easily take the food. It's a quantity available. So they are taking the food without realizing that the food is not at all contributing to their growth. So I have to say these predators are stupid predators. In fact, it is what happening in real life in our, or many of our real life also. We are going to, nowadays we are taking so much of junk food because we don't have other time, or we have to survive some food. We are taking the junk food, but the junk food is not providing any nutritional benefit to us. It's simply giving some energy but not any nutritional benefit. So we are having some other consequences. So this is something like that. So this is the way region D11, D12 and D2, D3 is always we have to avoid the region. And if you take any alpha xi in the region B11, B22, B31, B33, the solution will be driven to oscillatory state. That means we have a coexistence, but we have a oscillations comes into picture. But in any system, the oscillation will always be dangerous, because sometimes there can be catastrophic event. That means either completely predator can go extinct or completely the prey can go extinct. So oscillations we have to avoid. Generally, we will try to avoid the oscillations in the biological systems. In the region C11, C21, C22, C31 and C32, the solution will be driven to a stable coexistence. But the stable coexistence can be either prey dominated or pest dominated. So we have to see about how it happens, especially if you take C21 and C31, the dominator is pest predator dominated, but if you take in C22 and C32, that will be pest dominated. Because of some thing happening here, actually the orange color, this is called beta by delta, alpha less than beta by delta, alpha greater than beta by delta. This is what actually playing a role. So when my quality of the food is less than birth rate of predators by death ratio of birth rate of predators by death rate of predators, then the food is favoring a lot to the predators. But if it is more than the birth alpha is greater than birth rate by death rate ratio, then it is not favoring the predators, it is favoring the pest. So that's why we actually qualify or quantify the additional food as high quality if alpha less than beta by delta. Otherwise, alpha greater than beta by delta we term as low quality. And in fact, there is one more term beta delta by beta by delta into 1 minus 1 by gamma. If alpha less than this one, it is superior quality, we can say, because it is more faster growth will come into picture when we provide this type of food to the predators. And if you provide any alpha say in the region A11, A2, A1, A2, A3, the entire pest will be diverted to predator. The solution will be diverted to predator axis. That means the pest will be removed from the ecosystem. But the problem here is all the predators will go on the y-axis. That means we have an infinite growth. Mathematically, it is not acceptable, but biologically, we can avoid that by simply removing the additional food from the system, because the entire predator are depending on the additional food. So we are actually removing it. So we can see there are two different scenarios happening here. One food is helping the predators to survive and control the pest, and one type of food is actually giving a detrimental effects, such as it is actually favoring the pest and predators are getting extinct. So it is now, that's why I am saying this is double sword. It's a double-edged sword. We have one way we are actually having positive effect, one way we are having negative effect. So the same consequences will happen in the other scenarios also. But the first scenario we seen about without any competition or anything in between the predators. But in the real life, there can be competition, there can be cannibalism, lot of other things can come into picture. So if you want to investigate that, these are some simulation effects where actually the previous results, I'm just doing some simulation works. Not only that, this also provides me some control strategies. That means what is the quality and quantity I should take. We have a control fixed quality management recommendation. If you want a quality fixed quantity and varying quality, what are the various qualities you have to take? Or if you want to fix the quality and if you want to vary the quantity, what are the various quantities? Accordingly, what are the dynamics? What are the final steps we can have? But varying qualities in real life is really difficult, because we have to see about various different supplementary foods, which is really difficult. So, but varying quantity is somewhat easier because we are fixing the quality, but we can get a different quantities. So, this is more advisable control strategies. So, next we can have a polygamy in predators can lead to cannibalistic nature or mutualism. So that means they are trying to feed on their own juveniles. If they are feeding on their own juveniles, their actually reproduction will be going down and the predators numbers will go down, and that can be detrimental to the biological control. So how to avoid this? How to change the habit of cannibalism, or how the predators can be moved away from the cannibalistic nature, is to provide some supplementary food, because the cannibalistic nature is coming because they don't have the sufficient food for them. So provide some food, so avoid that. So how can I do that? Actually, whether this is good effect or not, actually there are some work done by Frank et al. In 2010 and provide some positive, semi-positive answer. That means sometimes this type of control can control the cannibalism, sometimes it may not be controlled. So again, there are two directions. So to see that one, again we are going to do some modeling effort, but actually cannibalism requires a stage structure modeling because we have a juvenile adults. But here, for the sake of simplicity and because all the dynamics we are going to take, most of them are short dynamics, because the prey predator system or the system will be, or the biological control will be of short dynamics we are having. So we are actually taking, instead of taking juvenile adult as a separate, we are taking them into grouping into a single predator population, and accordingly we have an equation comes into picture as this one. Dx by dt is x into 1 minus x by gamma minus xy by 1 plus x plus eta y plus alpha z. This eta y is actually represents the how the one predator is interacting with the interaction with other predator, intraspecific competition. And there is one more term you can see, minus rho eta y. This is actually the cannibalistic loss. Because of cannibalism, they are feeding on their own population, so there is a loss. So growth minus loss, so we have a extra loss is also coming into picture. So this rho is the cannibalistic interaction uptake, and in eta is the cannibalistic interaction rate. And these two also now we have three parameters. One is alpha, which is the quality, xi is the quantity. On top of that, we have one more extra parameter, that is eta. Eta is the cannibalistic rate of interaction. So the interaction is high means more cannibalistic interaction, if less means less cannibalistic interaction. So we have a three different parameters now. So how can you study this model? So that's why we again, if you remove this alpha psi again, it becomes a Benedictine de Angelis model. So again, we have a original model coming to Benedictine de Angelis. So again, if you do the equilibrium analysis, again it has one equilibrium point, it has one axial equilibrium point and one trivial equilibrium point, and there will be one more axial equilibrium point on the y-axis if the condition satisfied beta minus delta alpha xi minus delta greater than 0. And the system admits at most two interior equilibrium point, either 1 or 2, depending on various conditions. So after studying this equilibrium point and again doing the stability analysis, we have two transcritical bifurcation, one occurring at the carrying capacity on the prey axis and one occurring on the predator axis, axial equilibrium point, and 0 0 transcritical bifurcation, and there is a saddle node bifurcation because two interequilibrium point can collide and become an instantaneous interequilibrium point and then disappear. So there is a saddle node equilibrium point at the interequilibrium point, and we have a Hopf bifurcation. And as usual, the line alpha equals to beta by delta. So if you plot, and we have various other regions like gamma less than delta by beta less than and eta less than 1. That means the cannibalistic interaction rate is very low, and gamma greater than delta by beta minus delta, that is carrying capacity is greater than delta by beta minus delta, or eta greater than or equal to 1, that means high cannibalistic interaction. So we have a 4 different regions comes into picture. Draw them again, you can see that again we have a various regions comes into picture, and in the region E1 E2 the interequilibrium point, in this case the low cannibalistic interaction rate, we have this one scenario is this one, E1 E2 we don't have interequilibrium point, all the solution will reach to carrying capacity of the pest. In the region D we have a coexistence, and in the region C also we have a coexistence, but in the region C2 the coexistence is unstable. And in the region B we have a two interequilibrium point and comes into picture, and we have a this is what sorry, we have a one minute, that term I am missing that. We have a two interequilibrium point, one will be saddle. So we have a regions where one solution will be driven to pest free state, and another solution will be driven to the pest and predator coexistence state. So, and in the region A we don't have any interequilibrium point, and we don't have any pest interference. It is a pest free state.
So you mean the separatrix or something?
Yeah, it is actually that word actually now it is still in my mind. Actually this is what
Half bifurcation? Which one are
no,
you?
not a bifurcation. This is actually the word is actually how to use the word is 1 minute. Just give me a second. This is double equilibrium point. Actually, one is saddle, another one is stable. So we have something called
Pitchfork or transcritical or what are you?
no. I'm not talking about transcritical. The region I'm just oh sorry.
Okay, please go ahead.
Yeah, maybe I'll recall again that because it's my mind somehow it's got into this one. Yeah, so we have what is that? Yeah, okay. So again, in the case of again another region, again we can see that there are some others almost the similar regions, but even E2 we don't have any stable coexistence. It's pest dominated state, and D1 D2 we have coexistence, and C1 we have a coexistence, but again in C2 D3 we have a limit cycles comes into picture. But if you see here now, if you move from, if you fix a alpha in the region D1, if you fix alpha and increase xi, initially we have a stable coexistence, then we have an unstable coexistence, then we have a stable coexistence comes into picture. So we have actually having two times of half bifurcation is occurring. So one with respect to once we have a half bifurcation stable to unstable, again we are making unstable to stable. So at low prey population the stability comes into picture here. So this model is actually exhibited stable coexistence in the small limits prey population also. But this phenomena is happening in the previous case, because this is because of Asian food provision as well as the competition or intraspecific or the mutualism between the predators. Because of that, the growth is slightly reduced and they are not having any oscillations. And when eta greater than or equal to 1, we have only one case. We cannot completely avoid the pest from the ecosystem because of high cannibalistic nature or high mutualistic nature, but we can control them and we can keep them at a state where that is not damaging the crop. We can do that. That's the only thing. We cannot completely eradicate the pest from the ecosystem. We cannot do that. But this analysis also provides one more thing, is all the cannibalistic nature that we are taking till now is constant throughout the analysis. But generally it is not the case, because already we are providing the additional food to the predators. So when you provide additional food to the predators, the cannibalistic nature has to decrease. So the cannibalistic nature can be treated as a this is a simulations. Yeah, now I remember this is called bistability regions. This is what actually I am trying to talk about. Yes, this is called bistability regions, because if you have a two inter-equilibrium point, one will be saddle, another one will be stable or unstable. So, but because of saddle, that separatus will divide the entire region into two regions. In one region, the solution will go to one region, one equilibrium point. In other solution, it will go to another equilibrium point. So, this is called bistability regions. And this bistability regions are sometimes it is very dangerous, because sometimes we can have a oscillations, or sometimes we can completely remove one population also, which is not because slightly adding or subtracting one population, it can go from one region to another region and we can have a catastrophic events. So generally bistability regions we have to investigate, or we have to think very carefully when working with bistability regions. This is the word I forgot. This is called bistability region. Now, as I said here, the cannibalistic nature may not always is constant. It is actually because of Asian food provision, it is a decreasing function of the Asian food. So, while if you increase more food, the cannibalistic rate has to decrease. So, I can take n is something like eta bar into e power minus alpha psi. If I take like that, then we have a various scenarios comes into picture. So when you take this type of things, when you take alpha xi is something when I am taking this weak cannibalistic nature, that means I have a eta is less than 1, initially eta is less than 1 and I am providing additional food, so it is still reduces to eta less than 1. So what is happening is, if you see that in the first case I am taking alpha is 0.252, xi is 1. In the next case, I am increasing xi by 1.12. So that means I am fixing the quality but increasing the quantity. At the first step, you can see that this prey population or prey and predator population are actually going to stable coexistence. But when I increase the quantity, you can see there are oscillations comes into picture. If you still increase the quantity, then you can see that predator is dominating, prey is going down. Still oscillations are there, but still increase, you can see that the entire pest is going to 0 and the predator is surviving. So that means from coexistence, we introduce oscillations, and from the oscillations again we actually completely remove the pest from the ecosystem. That means we are providing some food which is favoring the biological control. This is actually alpha is less than beta by delta. This is the case in this case. This is a high quality food we are providing. Similarly, in the high cannibalistic nature also, previously we have seen that in the high cannibalistic nature, I cannot remove the pest from the ecosystem. But because if you treat that cannibalism as a function of decreasing function of alpha and psi, if you treat that position, you can see that you can increase the food levels, we can entirely drive the pest to extinct also. So even in the high cannibalistic nature also, we can achieve the biological control. But again, we have to provide the sufficient food provision or the quality we have to provide. Again, this provision is actually I am doing is high quality. If I provide low quality, the entire consequence will changes. So this is where I am discussing about the importance of quality. You can see that initially the prey is dominated, predator is dominated, pest is going to 0. So now I am increasing the quality, I am not changing the quantity, but I am changing the quality. Now you can see that there are some oscillations occurs into the pitch ecosystem. Now if you still increase the value of alpha, that means actually increasing alpha, we are decreasing the quality. Please remember that. It is the inverse. If the alpha is less, it is more quality. If alpha is more, it is low quality. So if I increase alpha value 1.25, that means I am providing low quality. You can see the oscillations are increased a lot. Then after that, after some time, everything will reaches to the carrying capacity. So the quality plays a vital role. So the provision of the quality or the food we are providing determines what we are going to do that. Whether you are going to drive the system to the pest dominated or you are going to drive the system to the pest free state. So again, that's why I'm again talking about double-edged sword. And again, we have a management recommendation depending on what are the various combinations of alpha and I can take. I can give you. So the eco manager, knowing all the growth rates of the prey, predator and their carrying capacity and all these things, they can feed the values and they can find the quality and quantity, what is the best quality and quantity by using these management recommendations. And this is where actually I am talking about the what is that ratio dependency like structure. You can see that the predator isocline going to 0, 0. This is what the one of the phenomena of ratio dependency. The predator isocline goes to 0, 0. But the prey population, we can have either stable or unstable also. But this type of behavior will not be happening in the regular Rosen-McMacarthur model or Bendit-DeAngelis model. Even if you provide additional food also, that will not happen. But if you include the cannibalistic nature or if you include the additional food along with the additional mutualism, then we have this type of scenario comes into picture. So this is one of the, I can say this is one of the alternative hypothesis of to ratio dependency. So that means already we are assuming the low prey population and predator population stable coexistence because of predators being generalist in nature or the polyphagous in nature, because they have a low prey population. To survive their numbers, they have to feed on other resources, during which the predation pressure on the prey will be relieved and they both will survive with the coexistence in a low prey population, stable coexistence they can have instead of oscillations. So this is one of the alternative hypothesis for alternative reasons for avoiding ratio dependency. So next we have one more. Vamsi, how much time can I have? Dr. Vamsi?
Sorry, I think my mouse got stuck. Maybe 5-10 minutes more, Prasad,
Yeah.
or you want some more time?
Yes, okay, just okay.
So,
Because I
Dr.
just
maybe,
discussed.
Yeah, 5-10 minutes more, you can take Dr. Prasad.
Okay. Then we have one more important concept comes here is polyphagous in pest. So till now we are discussing about only predators being generalist in nature or polyphagous in nature. But pest can also be polyphagous and they can also feed on the other resources than the crop resources. So in that case, the consequences become more complex because the providing food, nectar or pollen can be even taken by predators as well as pests. So they can also grow. Pests also grow using this additional food or they may not grow. So we have to see about the consequences. So accordingly, we can do the modeling approach. So we have dx by dt. So where there is a growth because of the prey is actually growing with respect to logistically and with respect to using some additional food. So we have a beta 1 h by 1 plus h is actually with respect to the resources and beta 1 eta xi x is with respect to the additional food. So we have alpha 1, alpha 2 is the nutrition quality with respect to predator, alpha 2 is the nutrition quality with respect to prey. So, but the quantity is same. We are not providing a different quantities for prey and predator. That is what we are assuming. But in next stage, we can do that also. That becomes more complex analysis. So we can divide that. We can only certain portion of Asian food will be taken by prey, certain portion will be taken by predator. We can go that also. But right now, we are providing the food in such a way that it can be taken by either prey or predator anytime. But the qualities will be different. That means the one food may high quality for predator, at the same time that may be low quality for prey or vice versa. It can happen also. That's why we have alpha 1, alpha 2 comes into picture. So now we have several things comes into picture, alpha 1, alpha 2, xi, 3 parameters. So you can see the complexity now what is happening. So again we can have a different scenarios, global dynamics. But here I am talking about alpha 1 xi space only because I am fixing the quality, because if I have to go for 3-dimensional, visualizing is really difficult, understanding is difficult. So what I am taking is I am taking the projection of this in the alpha 1 xi space by fixing alpha 2, fixing and then projection and taking, and I am studying the dynamics in alpha 1 xi space. So if you do that, you can see that if you see these are the same type of course what we have seen in the first model, but there is a slight difference. The blue curve is moving towards the alpha by delta or moving inside the alpha by delta less than alpha by beta. So because of quality effects on the additional food on the prey, either it can move, that means previously whether alpha greater than beta by delta, there is no coexistence. But because of the additional food taken by the prey pest, the coexistence comes into picture. And previously in other one scenario, we have seen that alpha less than beta by delta, alpha always coexistence is there. But because of the additional food levels or the quality of the food that is taken by pest, there can be no coexistence also. So various effects are coming to picture. So as usual, the regions are similar to the same thing. The best favorable regions are A, which is where I have the entire pest will be removed from the ecosystem. And this is the, you can see that what is happening. See that previously the diagram is similar, very alpha 2 is 1.5. It looks very similar to the picture what you have seen in the first case. This is without polyphagous nature in pest. This is with respect to polyphagous nature in pest. Now you can see that if you decrease alpha 2, you can see that region D11 is actually alpha 1 is moved to the right of that one. So the D11 is now split into some other regions. So previously there is no coexistence alpha greater than beta by delta, but we have a coexistence. In other words, I'll say that this is not favorable for my biological control. because I'm actually providing some food which is actually increasing my pest. Again, you can see that here in the other case, you can see that these two pictures are same, alpha 2 equals to 1. If I reduce, then you can see that we have a region where we have the blue curve is coming towards left of this one. That means even if I provide low quality food also, and even immediately it is actually becoming pest dominated. Again, this is also not favorable. So we have to see about proper quality and quantity what we are providing. So these are some simulations what actually for each of the regions what is happening. But main inference I am going to give you is here is this one. Even I can incorporate cannibalistic nature or mutualism nature in predators, mutual interference in predators. So the dynamics slightly changes. So we have a bistability regions comes into picture as we have seen in the previous case, because it's almost similar to that. That's why I'm quickly going through, but I want to show you the simulations where actually this is the case. Here the region actually I wanted region is A1, A2 is the prey reaches carrying capacity. Region G is the favorable region for where I have a pest will be removed from the ecosystem. Remaining all regions are stable coexistence or unstable or double bistability regions comes into picture. This is what actually the important application or important observation. You can see that I am varying alpha 1, alpha 2. In the first case, I am taking alpha 2 range is 4 to 0.5, alpha 1 is 1.533. So what actually I am doing is I am fixing the Asian food quality for the predators, but I am varying the Asian food quality with respect to the predator with different time intervals. So initially from 0 to 100, I am giving 4, then I am giving 2.0, then I am giving 2, then 0.5, then I am giving 0.25 after t greater than or equal to 0.5. So I am varying the quality for the prey. So if you see that in that case, what is happening here is, so initially the dynamics in such a way that both are coexisting, but prey is dominating, predator is okay almost, but after some time predator dominated, but prey is less, but at the end what has happened is the predator is going to extinct and prey is dominating. So this is what happening if you change the alpha. Now if you reduce alpha 1 to 1.2, then you can see the same scenario, everything completely reverses. Now we can see that the complete predator dominance comes into picture. Prey and predator both are surviving, but predator is dominating. Now if you slightly increase the alpha value 1.5333, then we can see that again, but now here the scenario is completely reverses. First initially giving high quality 4, I am giving low quality 0.5 and reversing. Then you can see that in this case I don't have any effect, both are same only. So even if I provide high quality to the predators or low quality to the predators, because initially I am providing a high quality to the pest, is not going to happen anything. It's not going to happen anything. The scenario is same only. So this is simulation illustrate that what is the importance of quality and quantity. You should be very careful about what type of food you are providing. If you are not providing proper food, that's going to be different consequences. So I'll stop here because it's almost 4:10. Maybe I have taken 5 minutes extra. Sorry for that. So if you have any questions, answers, I mean.
There are few comments, Dr. Prasad. Can you just see
Yes.
the comments? And then...
Comments. Okay, I have to see that in that case. 1 minute.
So a couple of them. Yeah, we started late, so it's not that you have taken 5 minutes extra. We started 5-10 minutes late, so we are on time.
Okay. So what is that? How to analyze the graphs? Sorry. How to analyze the graphs? Can you suggest any books for bifurcation graphs? Okay, generally this bifurcation graphs, all these things you can use. If you want a theoretical analysis, PERCO is the best book. PERCO, Dynamical Systems by PERCO is best book. And for other things, you have to use, what is that, books or something like, maybe you can see Strogach. And one more is, I think, one book I can suggest is uh, Dynamical Systems by, in Python by his name. I recall, just I'll search and share it in the chat. And one more, please share the PPT. Is it can be helpful for research? I cannot completely share all PPT because some work still is under review, so I cannot complete. Okay, but you can see the videos, online video, and you can use that one. But I cannot share the complete PPT. Sorry for that, because some work still under review right now. So, and the book, I'll just give you that. Any other questions meanwhile?
Any questions from the participants? Okay, if there are no questions, so let's all thank Dr. Prasad for taking his valuable time out and briefing us on the additional food provided predator prey systems. Thank you, Doctor.